We will now build on the first part of the voltage control. In the end of the previous video, we were looking at this delta Q, the reactive power lost during the line. And we have then, you can see these two equations. We call the two-port equations for reactive power, the Q1 and Q2. And we found out that the active power is sending this way to bus 2 from 1, and Q going from bus 2 to 1. And we could actually see that with the angle difference, and that V1 is leading V2, and also that V1 is lower in amplitude than V2. We can directly actually see which way the active power is flowing. The delta Q can then be expressed as the Q1 minus Q2, which Q1 is the reactive power injected at the sending end, minus reactive power absorbed at the receiving end. And we can then put up an expression, delta Q equals fill in here, delta minus x cos delta, like this. Let's see what we can do with this expression. And then delta Q, can put 1 divided by x outside, I think. Yeah, 1 divided by x. Then we have V1 squared plus V2 squared minus 2 times V1 cos delta. Yes, like this expression. And we often can, for many practical purposes, you can say that the delta is approximately 0, means that cosines to delta is approximately 1. That's a simplification you can do. And by doing that, we can actually get, because, and also, yeah, you can also remember that to have a relationship like this. Let's take it in green. A minus B square equals A square plus B square minus 2 times AB, like this. And we can recognize that from that equation above, as you see here. And then we can express this again as delta Q equals 1 divided by x V1 plus V2 minus 2 like this. So Q equals V1 minus V2 squared, like this. So we can now ask the question is how do we minimize reactive power losses? Yes, and the goal is then to have actually constant voltage in all buses, and also equal as possible. all buses in power network. So actually saying that if you have a uniform voltage profile, that will give the least losses of reactive power in the grid system. Maybe previously also have seen these equations very simple. Writing Q equals V squared divided by X. This comes from this relationship above here. Or Q can be calculated as X. Oh, X current squared like this. Very simple. So, but this implies that you see that the reactive power is very sensitive to the voltage drop of the system. So that is something you should remember when you go further now. Okay, we'll now start to look at what we call the central theorem for this voltage control. And let's see if I can have a big one separate now. So we're starting on new. And I will first draw a new diagram. Let's see. And then a bus here, a bus here. This is also a load P plus JQ, JX. And this is a E now. Yeah. Like this, so E. And then we have V. Yeah. Delta. We can call it the central dogma of power system analysis, or the central theorem. And it's a generator bus. We take as an example for the left hand side here, and then your load bus. So also remember that we have this short circuit capability I mentioned earlier. Short circuit capability at load bus. It can be expressed as I short circuit E on X or C E times ESC. Then we put this in here and we get E squared on X. Like this. So just remember this. That and I said that with the reactance becoming large, the short circuit becomes low value, and you have a weak connection point. Then write up the expression, the P equal minus E V X sine can be rewritten as EV like this. Now a minus because it's the load bus. I'm drawing power out. Q equals minus V2X plus EVX cos can be written as EV cos delta yeah, it's like this. And then we do a square of the equation and we sum the equations. Complete square. So this is a traditional math way to do it. And then let's go down here. Okay, we don't square it. E C square. No, sorry. Minus this pair now. Then we have the other one. E. Right hand side, we square can be multiply out as x squared q squared. Yeah. So then we let's see. Oh. Then we squared it. Let's sum right hand side and left hand side. Now, so and also do some simplifications. Let's move this. Yeah. Ready. E. Take the above first. Equals. Then we do a simplification. Let's take sinus cos outside. And then I take p plus 2x squared like this. Then we set it to equal 0 and we get squared plus 2 and the power, yes, p squared plus q squared equal 0. So what we did now was this became 1. Then we move this over here. And then we see that we have a common v square here and v square here. So it becomes outside and we sum it up in the parentheses. And then, and this will be the same here. So from this, we can actually see that this is a quadratic equation. So if we do it in that form, we can write it as, let's take it up, as, I put now y equal v squared. And then it becomes 1 times y squared x cubed is y plus q. And then this becomes a in quadratic equation, this becomes b, and this becomes a c. Yes, let's then write up the equation then, secondary equation. Times A. And this means like this. So here we have the quadratic equation, and we can actually write that we saying that we have a physical solution if, and then we look what's under here, square root. This is probably familiar with before, but if you're saying that this should be greater or equal to 0, it can be not negative under the square root. So that this is something we know to have a physical solution. So 2xq minus e squared minus 4x equal to 0. That's an important thing if you notice. Here. We can then simplify this even a little bit further. So let's see if I take here. I can write this as 2 squared if you take out from this parenthesis. Squared q squared minus 2 q e this is this comes from here. Then we can write up the whole, will be something like this, 4x here minus 4x cubed e plus minus 4x p squared minus 4 x squared q squared. That's 0. Like this, then I would take in the whole, and we can divide on yeah, let's see, 4x square, I think. Yes, let's do that. And then we will have the expression q squared minus q squared x plus, yeah, e squared 2x and I take the whole and square, yes, minus p squared minus q squared larger than 0. Then this goes away. I can actually write this finally as, take the blue, minus p minus q over x e squared. Sorry, plus is now 2x squared larger than 0. This is the traditional way to write this out here. The physical solution is more readable. So we can then find the limits of such a transmission system. We can then, it's right here, the limits. So if we then start with, so we put it as to 0, let's do that. Then we have minus p like this, or it can be written as minus p minus plus squared equals 0. Then we divide on the short circuit ratio, which is e squared divided on x. I guess you use that a lot now. If you do that, we will get minus p. Yes, yeah, I've forgotten the square here, I think. Yeah, and also up here. Sorry about that. No, it's right. Minus p squared. Like this. And then it goes away. This goes away. And of course, there. Now you'll continue. Like this. Equals 0. Then we again do this, divide on that, and then we get, see, get here, minus, no, 0. Now we're closing in. This means minus p2 x. Oh, sorry. Here comes qx. 0 plus 1/4 equal 0. And again can be written as px squared minus qx Then I come to the equation I was looking for, where you can look at the limits for such a transmission line. So we could also, of course, write it with the short circuit ratio. So as you remember, the SS on X, this form. And then we could write it like minus. You can see also some literature are using all of this. Like that. Minus Q plus 1/4 quarter. And Q divided by equal 4 minus P like this. I think that is the final form we can have on this. You can see some, as I said, some books are using that form. However, I think I will just use this one and see on some limits here. Oh, sorry. Let's see one more time here. So let's first start with if we see P, if we're setting then the P equals 0. So this expression here becomes 0. That means that Q be lesser or equal to E squared divided by 4x. That's the first limit I wanted to look at. So the maximum of purely Q load here is 1/4 of the short circuit power. And if we take Q equal 0, we will then have the expression as P less or equal to E squared divided by 2x from the same expression. This implies that it's a half of the short circuit power, the 2, and this is the 4. So this relationship comes then from the induction nature of the transmission line. That's important. And large Q support is required with large P, will result in a high load plus voltage often. We can draw this diagram. Here we can see the reactive power versus active power divided on short circuit ratio. So the physical solution we will have in this region here, and with a non-physical value here. It also indicated the maximum value you can have here, 1/4. When the active power is 0 at this point, we have that max. So when reactive power is 0, we have that value. This is if you plotting down this equation here. So with this I end this part 2 of the voltage control.